Good and welcome to this video on question 5 of the 2013 Scholl Calc exam. This question here had an optional component to it. Part A was compulsory, involving a tethered goat. I'm going to look forward to making the thumbnail for this one. But part B had an either or option, either a linear programming question, which is quite short, or a critical path question, which is also quite short. Given that these are based on the internals that don't seem to be examined, if you're watching this a few days before your exam, maybe try your luck and just focus on your externals and your trig and your conics. But looking at the first question, we're going to, of course, solve the problem, but we're also going to look at how the function for the area was derived, just as an aside. And we'll start there now. Okay, it looks like an absolute mess of an equation. I'm kind of gutted that the examiner didn't ask the students to derive it, because it's doable, but I guess if you didn't derive it correctly, then your answers for the next part would be all wrong. But we've got this goat here tethered with a rope of length R to a point P. So the fact that there's a fence there blocks the goat from being able to access all parts of the paddock. So it roams freely around in a circle as far as possible around, but when it gets to this point here, it doesn't continue with the circle because the fence shortens the rope and cuts it off. Likewise, if the post P was all the way over here, then the goat could run around in circles and the fence wouldn't come into play at all. We've got a region that the goat can graze in made up of a fraction of a circle. Okay, if you just look at the Pac-Man kind of thing, it's a total angle of 2 pi minus theta. That fraction of the circle the goat is able to access no problems, and the circle has a radius of r. So that is this bit here, 2 pi minus theta, that angle divided by the total angle. As I said, it was a fraction of a circle, 2 pi minus theta all over 2 pi, that fraction of the angle, 2 pi is 360 degrees, times pi r squared, the area of the full circle. The pi's cancel, and that's where that 2 pi minus theta all over 2 r squared comes from, fraction of the circle. Then we've got a triangle. You need to note that this is r, and the area of a triangle is half base times height. So to find the area of this triangle, we're going to go area is a half times base. The base of the triangle is going to be this length r cos theta, and the height of the triangle is going to be this length r sine theta. So we've got r cos theta times r sine theta, and that's a half r squared cos theta sine theta, which is of course the last term of this expression here. And how do we get the middle term? Well, that's the small little circle, a quarter of a circle, there. It's a quarter of a circle, but the radius is different because it's shorter. The radius of the circle is this length, which is the full rope's length, r, minus the length from P to the fence. So the area of that is a quarter of a full circle, pi with a radius of r minus r cos theta, pi r squared there. So, and then a bit inside we can pull the r out the front of it. So it's going to be pi r squared over 4 times 1 minus cos theta all squared, and that is equal to this. Okay, so that's how the function itself is derived, but they've just given you the function and said find the value of theta where the area is minimized, so where the goat has the least amount of grass to be able to graze. So we need to differentiate this and make it equal to 0. And that's where we will start. Okay, area, 2 pi minus theta, all divided by 2 times r squared, plus pi r squared over 4, 1 minus cos theta all squared, plus r squared over 2 times sine theta cos theta. The variable's theta, r is the constant, it's the rope. We're assuming that the rope doesn't change length while the goat is trying to get free. It's a constant length. We'll assume that it's at the maximum length it can be. The first term there is a linear function. If I put brackets around that, it makes it easier to see. We've got 2 pi over 2, or pi times r squared. When we diff it with respect to theta, that disappears. And then the last term of that brackets is minus theta over 2 times r squared. And when we diff that, it's a linear function, so it diffs to minus r squared over 2. The second term, the constant pi r squared over 4 just sits in the front of the expression. We use a chain rule to differentiate the thing squared. 1 minus cos theta all squared. The 2 comes down the front of those brackets, but power drops to a 1, and then we times by the inner derivative. Minus cos theta differentiates to sine theta. And then the last term, r squared over 2 sits in the front, and you could use the product rule to differentiate that, or you could use a trig identity to turn it into a double angle expression and then diff. I'm going to use the product rule because I don't want to bring in double angles. I've got to solve this equal to 0 eventually, and if I've got a mixture of angles theta and double angles 2 theta, it's going to be a bit of a mess. So let's just use the product rule. So this here is my f, and there's my g. So f dash is cos theta times g, which is cos theta, so I get cos squared, plus the derivative of cos theta, which is negative sine, times by the first sine, so cos squared minus sine squared. Okay, and that's equal to 0. Finding the minimum area. Now, we can, because it's an equation, we can times everything through by 2. Actually, 4 would be nicer. It's times everything through by 4 and divide everything by r squared. So times by 4, divide by r squared, everything, that becomes minus 2 plus pi actually no, I don't need it times by 4 because there's I missed that little 2 that's in there. So if I times by 2 over r squared, yeah, that's better, minus 1 plus pi 1 minus cos times sine, and then the last term, the r squared over 2 disappears because I'm timesing by 2 over r squared. And we've got to solve this equation here. This is quite a tricky equation to solve because it's got a product of cosine and sine. It's got the quadratic expression as well. There's a couple of ways you can do it. You can use the identity sine squared theta plus cos squared theta equals 1 multiple times. You can use it once to get rid of, say, maybe that cos squared, and you can use it again to maybe get rid of this cos theta here, and that turns the problem into a quadratic. So I'm gonna try this as an approach, but there is a different way of solving it as well. So if we go minus 1 plus pi, okay, the 1 minus cos theta bit, I'm going to write it as 1 minus the square root of 1 minus sine squared. Okay, because instead of cosine theta, I can rearrange that trig identity and get rid of it. And then the other one, I can get rid of the cos squared theta in the last term, because I can write it as 1 minus sine squared theta. And I've got another minus sine squared theta, so 1 minus 2 sine squared theta. And now I want to solve this for theta. And the reason why this identity has actually been quite nice to us is actually the plus 1 there cancels with the minus 1. So we start off with an equation with 3 different terms in it. Oh, actually no, 1, 2, 3, 4 different terms in it, but 2 of them have cancelled. So I've got pi times 1 minus root 1 minus sine squared theta times sine theta equals 2 sine squared theta. Sine theta is not 0. Okay, sine theta would be 0 when theta is 0 or pi, but if we go back to the goat here, if that angle theta that's in the diagram is equal to 90 degrees, no, it's not 90 degrees, 180 degrees, what does that mean for the post? It's infinitely far away from the fence. And if the angle was 0, then the post is right up against the fence. So both of those are maximum areas where the goat can, if the post is here, the goat can do a full circle around the fence. Can't get through the fence, but it can graze a full circle. And then if, like I said earlier, if the post is far enough away from the fence, so both of those are maximum areas. Sine theta doesn't equal 0, so we can cancel 1 from both sides. Now we can square both sides of this. But first up, I'm going to rearrange it so the square root's the only thing on that side before I do that. This is probably one of the hardest trig equations I've seen in scholarship over the last number of years. I'm going to square this, expand it and then move the pi to the other side. So it's 2 sine theta minus pi. And then I've got minus pi root 1 minus sine squared. Now if I square both sides of this, I've got pi squared times 1 minus sine squared. And then the right hand side I've got 4 sine squared theta minus 4 pi sine theta plus pi squared. And this is a quadratic equation, so I can make it equal to 0. 4 sine squared on the right hand side with another pi squared sine squared, so 4 plus pi squared times sine squared minus 4 pi sine theta, and then I've got a pi squared on both sides which cancel. Pi squared there and a pi squared there. Again, sine theta is not equal to 0, so I can divide through by sine theta or factor it out. Let's just factor it out. So I've got sine theta factored out, 4 plus pi squared times sine theta minus 4 pi. Sine theta is not 0 as I was saying, so that means 4 plus pi squared times sine theta must equal 4 pi. Sine theta must equal 4 pi over 4 plus pi squared. And theta we can assume is an acute angle. Theta is the sine inverse of 4 pi over 4 plus pi squared. Okay, so if we take the sine inverse of that, I'm in degrees on my calculator, so just so that I can visualize what the angle is. Comes out to be 64.96 degrees. Just checking the schedule to make sure that that's what they have, because in the schedule they solve the problem in a completely different way. They have they come out as an expression of 2 tan inverse of 2 over pi, which is, I guess, much tidier than my expression. But is it the same? Yep, cool. So what they did, which was a bit more conventional than my method, is rather than use the trig identity sine squared plus cos squared theta equals 1, they turned this part here 1 minus cos theta actually they did use the identity on this one, but they turned the 1 minus cos theta part using the double angle formula into minus 2 sine squared theta over 2. They used the double angle formula backwards, and they also turned a sine theta. They turned a sine theta part into 2 sine theta over 2 cos theta over 2, which enabled them to factor a sine theta out of 2 out of some terms. Personally, I don't see that as an obvious way to solve that problem, but it comes out with a fairly nice solution. My method was a fairly reasonable trig identity to use, but it brought in a square root. And so whenever I bring a square root in, I go, I'm going to have to square that equation. I was just lucky that the minus 1 cancelled with the plus 1, and that equation could be rearranged before squaring. But they would give you, if they gave you something like this in scholarship, they would give you an equation that you could actually solve without reaching for a calculator. And the only point that I reached for a calculator was at this last step here, when I wanted to know what the angle actually was. And it's not a special triangle. The ratio 4 pi over 4 plus pi squared it's not like 1 over root 3 or something that's nice. So I reached for a calculator to get the angle. But I could have written it and left it just as this. That's the exact answer to the problem. Okay, part B, as I was saying at the start of the video, has an either and an or. The first one's quite an easy linear programming problem. We've got some constraints. If you've never done linear programming before, this is not the video to help you with that. But first thing is we need to graph those constraints. We're told a is a positive constant, so x is less than or equal to 2a. I don't know, let's just make a 5 for the benefits of this diagram. So we've got, it'll be x is less than or equal to 10, so we shade out that way, and then it'll be y is less than or equal to 15. Let's just move it to 2a. Not to scale, I've already stuffed up the scale. And then x plus y is less than or equal to 4a. That has intersection points at 4a and 4a. So it's something like that. It turns out that there's intersection points here and here. The intersection points, if y is equal to 3a, then the x value must be a. For the sum to be 4a, and then at this point where the x value is 2a, the y value must be 2a. Okay, so the first mark in the mark schedule was for the points of intersection. also for the feasible region a second mark. So we've got points of intersection at A, 3A, and 2A, 2A. Now, if we're trying to optimize something, we're asked to graph an objective function. The coordinates that optimize it are usually the furthest away in the feasible region, and we're asked to, in the question, draw a nonlinear objective function for which there are exactly 2 points in the feasible region which maximize the objective function. So the easiest way to solve that problem is to go, let's say these two coordinates we've got are the maximums. Then if we have a nonlinear, an objective function like this, those will be the last 2 points that are reached in the feasible region. So they must be the optimal points. So that's the example that we need to give, and that is the answer. Okay, if we had a nonlinear objective function, like I'll draw one that's wrong. So if we had something like this, okay, then all points that are along that line inside the feasible region, of course, the points have to be inside the feasible region. So something like all these points here, they're not optimal because there's points in the region that would generate a higher value of, and then we want, and there's an infinite number of points. So to get 2 points, we want the objective function to go through the 2 vertices that we've got. This is one example, but the green is the answer. Okay, the last question here, the alternative option was to do critical path, and we've got a series of tasks about painting 2 small rooms. The painters realised that they could complete the job faster by working on each room separately, and they started a new plan. Discuss how much faster the painters might complete the task and any real-world limitations that may restrict them. So for a start, if we just go through the first option in figure 4 and work out how fast it actually takes them. Personally, I don't set out my critical path networks like this, as flowcharts like this. But if preparing the rooms can't be done until the material and the moving of the furniture is done, then the preparing rooms can start at 40. It has to wait for the moving furniture, which takes longer. And therefore the painting of the rooms can start at 70. And then the tidy of the rooms can start at 150, and so can the painting drying. 150 plus 30 makes 180, but returning the furniture has to wait for the paint to dry. So 150 plus 240, 390 is the earliest that the returning of furniture can happen, and then 30 makes 420. So that is how long it takes in minutes under the first approach. The painters realised that they could complete the job faster, and they start a new plan. Discuss how much faster they might complete the task. So the buying material hasn't been split, so we keep that at 30. It does say here that the figure was reproduced in the answer booklet for you to annotate over it. Moving furniture from room A and moving furniture from room B, let's assume that the rooms are of equal size and equal amounts of furniture in them. So 20 minutes for each of those. And what that would mean is that room 3 could start preparation as soon as the materials have been bought, so it could start at 30. And room B could also start as early as 30, because we don't have to wait for the other furniture to be moved. The painting of room A could therefore start as soon as room A has been prepared, and the rooms take 30 minutes to prepare earlier. So assuming that the rooms take equal amounts of time as well, then the durations are 15 for each of them. So we could start painting room A at 45 and also room B at 45. This is assuming that we've got people working in both rooms at the same time. And if they've got two people working in one room versus one person working in one person working in the other, the times are different. So there's a lot of real world assumptions that we're making here that limit what we're doing in terms of time. Tidying room A, sorry, the painting's 80 minutes, so let's assume it's 40 minutes for each. Could put some brackets around there so that's clear the durations I'm talking about. So tidying room A could start at 85. Painting drying from room A could start at 85 once it's painted. So this one 85, this one 85. The tidying of room A, well, tidying rooms takes 30 minutes, so we'll assume that it's 15 for each of the rooms. Painting drying though, painting drying takes 240 minutes. It's not going to be shortened when it's not going to be 120 for each room. The paint's going to take 4 hours. That's 240. I'm sure that would have been a trick that a number of students would have missed. So that's the longest part, right? So it doesn't matter where the tidying of the rooms happens. We've got to wait for the paint to dry. So 85 plus 240 is 325. That's the earliest that can start. And returning the furniture, again, we'll assume half for each, 15 minutes, 15 minutes. That takes us to 340, the end. So what we've done is saved 80 minutes. In the mark schedule, they talk about real-world limitations. I was discussing a few as I was working through that problem. They've got, assuming the rooms are the same size and the tasks are divided equally, they've said splitting out the moving furniture task makes the buying material task part of the critical path. So we haven't actually talked about the critical path at all in this answer. But if we go for the original problem, starting, moving furniture was the critical event. Buying material had ability to be delayed. It only took 30 minutes and it didn't have to be finished till 40. So moving furniture was the critical task. Preparing rooms, painting rooms were critical. The tidying the rooms, well, that didn't have to be done straight away because the painting drying was the one that took ages. That was the critical task. So the critical path there was highlighted in green. When the moving furniture is chopped down to 20 minutes for each room, the buying material becomes the critical task. It's the longest one there. Then the preparing of rooms, well, they're both critical, starting at 30 each. Painting rooms starting because the painting needs to, painting of both rooms needs to happen before the paint is able to dry, and then the returning furniture follows from that, and then the end. So the network changes with respect to the critical path. It says splitting the tidying task does not help because the paint drying takes much longer. It says the painters might need to spend more on material if they're painting 2 rooms at once. Good point. There might not be enough painters to paint 2 rooms at once, or to move the furniture twice as fast, or any other comment that you might come up with. But the basic maths of the question is we've shortened it from 420 to 340 minutes. But there's a whole heap of limitations there that would stop that probably happening. Catch you on the next video.